Before we get into the video tutorial, let us first take a look at these three learning goals. Learning goal number 1. I can identify a damped harmonic motion problem by looking at the equation. Learning goal number 2. I can take the derivative of a function using product rule. And learning goal number 3. I can solve optimization problems by finding the maximum and minimum values of a function and its derivatives. These learning goals are the most important takeaways from this lesson, and we are going to use them to solve a problem a little later on in this video. Let us first start off by reviewing each learning goal, starting with damped harmonic motion. Damped harmonic motion problems are oftentimes represented by a function that includes an exponential function multiplied by a trigonometric function. The most important thing to note with damped harmonic motion is that for every crest and trough, the amplitude is always changing. So now we move on to our second learning goal, which is product rule. And product rule is applied to get the derivative of a function when two functions are being multiplied by each other. And as you can see here, we have the general equation listed below. And finally, we have our third and final learning goal, which is optimization. Optimization problems require you to find the minimum and maximum value of a function and its derivatives. To find the maximum/minimum values of a function, you must find when its derivative equals 0. Similarly, to find the maximum and minimum values of the first derivative of a function, you must find when the second derivative is equal to 0. So now that we've reviewed all our learning goals, let's get into the question and see what we can apply where. Now, finally, the moment we've all been waiting for. As you can see here, we have the world's best calculus question to work through during the rest of this video. Let's start off by reading it. A bungee jumper's height above the ground in meters from jumping off a bridge can be modeled by the equation f of x is equal to 7e to the negative 0.116x cos x plus 5, where x represents time in seconds. Using the equation above, answer the following questions. A. Will the bungee jumper hit the ground or is it safe? B. The bungee jumper's wife is on a viewing platform 5.36 meters below the bridge. Will the bungee cord bring her husband high enough for her to snap the perfect picture? The time for the perfect picture is when the bungee jumper stops in midair. C. What is the magnitude pop pop of the bungee jumper's maximum velocity? So now that we've read the question, we're going to get into part A. So before we attempt part A, let's first break down the problem. So first we need to recognize that this is a damped harmonic motion problem because the equation clearly shows an exponential function multiplied by a trigonometric function. Second, we recognize that we are going to have to use product rule to get the derivative. And this is because it shows two functions, an exponential and a trigonometric, being multiplied by each other. And third, we're going to recognize it's asking for the position of the jumper, so we're going to have to optimize the original function by finding when its first derivative is equal to 0. So to solve this problem, I need to take the derivative, and to do that, I start by splitting my function up into two parts. So I have my g of x, which is the exponential part from the original function, and my g prime of x, which I got using chain rule. Now I have my h of x, which is cos x from the original function, and h prime of x, which I got using trigonometric derivative rules. Now you can see here I have my general equation for product rule to get the derivative of this function, and I'm going to plug in all the values that I just found. So now in this step, I common factor out this value, and then I make the first derivative equal to 0 so I can isolate for x. Now that I have my x value, I'm going to apply the cast rule, And I use quadrants 2 and 4 because the x value is for when tan is negative. So here I use the x value from option 1 because maximum displacement in damped harmonic motion problems occurs during the first drop, so that would be the biggest risk for the jumper to hit the ground. Now I plug that x value back into the original function. So now we can write our therefore statement. Therefore, the bungee jumper will be safe and will not hit the ground because the value of the maximum vertical displacement of the jumper is a positive value. And as you can see here on the visual representation from Desmos, the first drop, the Rx and Y values match up with the function on Desmos perfectly. So this proves our answer is right and the bungee jumper will not hit the ground. So now let's break down the problem for part B. So essentially it's the same thing as part A. We've already recognized it's a damped harmonic motion problem. We know that we're going to have to use the product rule to get the derivative. And finally, this part of the question is also asking for position, so we are going to have to optimize the original function by finding when f prime of x is equal to 0. So again, very similar to part A. So as you can see here, I carried over my x value from part A because it will be the same. I then go on to calculate the height of the bridge by making x equal to 0, so I get 12 meters for the height of the bridge. And then to get the height of the platform that the bungee jumper's wife is standing on to take pictures, I do 12 meters, the height of the bridge, subtract 5.36 and get 6.64 as the height of the platform. Using my x value, I apply the cast rule twice to the C quadrant. I do this because the platform is above the equation of axis, which is 5 meters, so I know it's going to be a maximum value, and the C quadrant produces my maximum values. Now I plug the x values I just found into the original function and do a bit of a guess and check. I am looking for one of these x values to produce the height of the platform. You can see when I plug my second x value into the original function, it matches the height of the platform. This means the bungee jumper will stop directly in front of his wife for her to take the perfect picture. So now we can write our therefore statement and say therefore the bungee jumper's wife will be able to take the perfect picture of her husband because he comes to a stop at the height of the platform where she is watching from. And again, just like part A, the Desmos representation of the function here confirms our x and y values, meaning that our answer is correct and she will be able to take the perfect picture. So again, similar to the other parts, we're going to start by breaking down the problem. So the first one is the same as the other two parts. We know that this is a damped harmonic motion problem. However, the second one is a little different. Because we're going to have to take the second derivative, we're going to have to apply the product rule twice. And third, we recognize that it's asking for the magnitude of the jumper's maximum velocity. So we are going to have to optimize the first derivative by finding when the second derivative is equal to 0. So now that we get into solving part C, as you can see, I just took the first derivative from part A and I'm going to split it into 4 separate functions. G of x h of x, I of x, and j of x. So now to get the second derivative, I'm going to apply the product rule twice. So I start here with g prime of x, and I got this by applying the chain rule, and now I just slot in h of x and subtract g of x, and again I have my h prime of x, which I got by doing the trigonometric derivative rules. Now I have my I of x, and I'm multiplying it by j prime of x, which I also got using trigonometric rules, and now I get my I prime of x, which I got using chain rule, and there's just my j of x from the first derivative. So in this step here, you can see I've common factored out this value to kind of simplify my equation so I can isolate for x. So here I just collect like terms to simplify the equation a little more, and I continue to isolate for my x value. So now that I have my x value that represents when max velocity occurred, I plug it into the first derivative equation to get the magnitude of the maximum velocity. So finally we can formulate our therefore statement and say therefore the maximum magnitude of the bungee jumper's velocity will be 5.9924 meters per second, and we don't care about the fact that it's a negative velocity, we only care about magnitude. And as you can see, the Desmos function confirms our answers by having the same x and y values. And just like the screen says, that's all folks. Thanks for watching this instructional video on how to solve damped harmonic motion optimization problems using product rule. If it was helpful, please like and subscribe to the channel for more content like this.